All right, so welcome to another installment of ModSim videos. You're joined by Mark and Rohanna today.
Hello.
And now that we've introduced this idea both of sort of generally thinking about conservation to derive a partial differential equation model and also thinking about different types of flux in deriving that partial differential equation model. In this video, we're going to do an example of actually trying to figure out a PDE model for a physical situation. And you'll be delighted to know we're not going to talk about an iron bar in this situation at all. Rohanna, I know you really love that iron bar, but
what are we going to talk about?
Well, why don't we talk about something that looks like an iron bar but is different. So what you will wonder is this. No, it's not an iron bar. This is actually a pipe, but it's a pipe that's closed.
A hollow iron bar.
It's a hollow pipe or a hollow iron bar that is closed at both ends. Yeah, you know, when I was in the partner year, there was a time when there were a set of students that were, two sets of students that were building golf ball cannons. One set of students had had an enormous amount of experience building things. The other set of students knew nothing. And when I said knew nothing, one of them actually went to a student on the other team and said, "Say, Brett, is there can you buy sort of like a metal cylinder with a hole in the middle?" And Brett said, "Yeah, Joy, that's called a pipe." So anyways, this is a pipe, and it's a pipe that's fixed at both ends. Sorry for that little bit of Olin trivia there.
I might have been in that second group of students.
Yeah, but that second group of students actually built a golf ball cannon that kicked the ass of the first group of students, which was pretty entertaining. So if you want to know that story, I'll be happy to tell you more, but that's not what this video is about. So we've got this pipe. It's fixed at both ends. It's filled with water, right? So there's water in here. And I've got a little port on the side of the pipe. And into that port, at time equals 0, I inject some dye. Right? So initially, I have just this disk of dye that's right at the center. Right? Okay. And of course, if you think about it, what's going to happen is that dye is going to spread out through the pipe. So over time, the dye will spread out. And eventually, I'd imagine all the pipe would be filled with the same sort of color of water. Right? So what I'm interested in asking, though, is how do I model the amount of dye, the number of dye molecules, as a function of position and as a function of time in the pipe? So in order to do that, I'm going to derive a partial differential equation for that. To derive that partial differential equation, the first thing I need to do is just figure out what quantity I'm trying to figure out. So what I'm trying to figure out, I'm going to call psi of x and t, and this is the number of dye molecules per meter cubed at a given point along the pipe.
Okay.
Right? So as I move along the pipe, psi changes. So initially, my initial sort of configuration is psi is 0, 0, 0, then it has a spike here, and then it's 0, 0, 0. Does that make sense?
So we start measuring from the left end.
Right. We'll call this x equals 0 and this x equals L. Okay. Does that sound good? Mm-hmm. Okay. So in order to figure out the partial differential equation here, we're going to use an approach that's similar to what we used for the heat approach. So we're going to think about just some arbitrary chunk of the pipe that runs from the point x equals A to the point x equals B. Right?
Okay.
And the first question I want to ask is, how much dye is there in this chunk? So how would I figure that out, Rohanna?
Something about how much dye is coming in and how much is coming out?
Well, certainly the amount of stuff that's coming in and coming out might change the amount of dye in the chunk, right? But if I wanted to actually just ask how much is there at a given instant, probably the easiest thing to do would just be to add up the total number of molecules in there, right? That's such an obvious statement that it has to be not obvious. So the amount in there, right, I could pull out sort of calculus ideas, right? It's going to be the integral from A to B of the density of the dye, which is a function of position and time, right? So I do actually have to integrate psi along that, times the cross-sectional area times dx, right? So that's the amount in the dye. Now that amount is going to be changing in time, right? And the way that amount is going to be changing in time is, as you said, because things are coming in and things are going out, right? So if this is the first side and this is the second side, I could have some flux of dye particles coming in on the left, right?
Sure.
And I could also have some flux going out on the right, right? So the time rate of change of the amount of stuff in there, the time rate of change of the dye molecules in that slice is going to be the flux coming in from the left minus the flux going out to the right.
Sure.
And notice that this is just assuming that positive is to the right. If I had a negative, if I had particles going out to the left, that would just make phi sub a be negative. Mm-hmm. So this is a general statement. It's not assuming that the particles are moving in either direction.
That's just what I was wondering.
Right. Okay. So now that I've got that, right, if I look at this, right, you'll recall that what we did in the case of the heat equation is said, well, wait a minute, this, the difference between these two things, that looks sort of like the integral of something. In particular, it's negative the integral from a to b of the derivative of that flux with respect to position, right? That's just fundamental theorem of calculus.
Sure.
Okay? And notice that I have chosen to write a partial derivative here because, of course, this flux might change in time as well as changing in space. So I need to actually just take the derivative with respect to doing this at a snapshot in time. So I'm holding time constant and just asking the question at that instant, how is flux changing in space?
Okay.
Okay. So now what I did is I said, okay, well, the only way that this left-hand side can equal that right-hand side if I bring the derivative inside, right? And if I bring the derivative inside, I have integral from a to b of the partial of psi dt times a, which is a constant, times dx has to be equal to negative. The partial of phi with respect to time is that the time rate of change of the particle density must be equal to the negative spatial derivative of the flux, right?
Yes.
And I think I probably have a unit issue running around here. I think I forgot an a, right?
Because you did indeed.
So there's my a, but I think everything else is kosher there.
Okay.
Does that look kosher to you?
Mm-hmm.
If it doesn't, please stop me because I'm
So
always
so
happy to make mistakes. All right, so
So
this is
far, so
this
good.
is actually the same thing that we got to back when we were doing the heat equation example, right? And at this point, we now need to actually get a little bit more specific and say, okay, how do we think about what this flux is? What's an appropriate model for that flux? So you recall that in the previous two videos, we actually talked about two possible kinds of flux models. One possible flux model is advection, and one possible flux model is diffusion. So do you have an opinion, Rahana, about which of these would be appropriate to use in this case?
Advection means drift.
Advection means drift, right? Drift is another word that people use for advection. Advection is associated with actual bulk motion of the fluid.
And this would be the particles diffusing through the fluid?
Yeah, in this case, the fluid is not moving, right? It's
Right.
water that's fixed in this pipe. So there is no advection present. It's purely diffusion that's present. And since it's purely diffusion that's present, we can go ahead and recall what we did when we figured out diffusion, right? When we figured out diffusion, what we saw was that the actual diffusion flux is given by minus the area times some diffusion constant, and that diffusion constant depends on what the material is, times the spatial rate of change of whatever the physical quantity is that you're talking about. And so in this case, it's going to be psi,
Okay.
right? So my flux here is the partial of psi with respect to x. So if I actually go ahead and plug that in, I'm going to get a times the partial of psi with respect to time is equal to a times d times the second partial derivative of psi with respect to position squared. Of course, I can cancel out the a's here, and I get my equation that the partial of psi with respect to time is a diffusion constant times the second derivative of psi with respect to position. Okay, now, before we finish this video, let's just take a second to look at that equation and see whether that equation makes any sense. So I'm going to go to a new page, and we'll write that equation down. So let's think about some point in the bar, or in the, it's not a bar, it's a pipe.
It
right?
is a hollow bar.
It's a hollow bar. And let's think about some point where at some point in time I have a concentration that looks like this,
Okay.
right? Okay, so what, first of all, ought to be happening to the concentration at, say, this point, according to this expression?
The concentration Does it go down?
Well, it says that the time rate of change of the concentration is proportional to the second derivative of the concentration with respect to position, right? And let's be explicit that we're plotting concentration versus position here at a given time. So at that point, the concentration actually ought to be dropping a little bit, right? What about at this point here?
Looks like that second derivative is
positive, right? There's a curvature, so the concentration should be increasing here, and at this point, in fact, it shouldn't be changing at all, right? Because the second derivative is 0. So in fact, this says that a little while later, it probably ought to look something kind of like that, right?
Yeah.
Which sort of makes some sense. You could also ask the question, why is it that if d squared psi by dx squared is 0, do we get no diffusion? Because clearly there's a concentration gradient there, so it seems like there should be, but why doesn't psi change in that case? And the reason that psi doesn't change in that case, if we plot psi versus position, for that no second derivative means that psi is linearly decreasing in space, right? Which means that the amount of diffusion flux from this side is equal to the amount of diffusion flux on the other side, right?
Okay.
So the amount that's coming in is the same as the amount that's going out.
Sure.
And that's why psi is not changing at this point in space, because the amount coming in at that point is the same as the amount going out at that point.
Okay.
So at this point, we have our partial differential equation that describes this physical situation. And in the next video, I think what we probably should do is ask the question, okay, what the heck can we do with that? How do we actually tie that to the physical situation? Because this right now is purely a statement about what is locally true about psi. At each point locally in this bar, it is true that the time rate of change of psi is proportional to the second derivative of psi in space.
And we want to think about what happens in aggregate?
Well, we'd really like to know, ultimately we want to know what happens in aggregate. Ultimately, we'd like to know what happens at each point along the bar and at each point in time. And in order to do that, we need to know not just what happens at a sort of arbitrary point along the bar or along the pipe with a hole in it, the bar with a hole in it, which is also a pipe. We also need to know some stuff about what's particularly true at time equals 0, what's particularly true at the left hand and at the right hand end. We need to know about some things called boundary conditions and initial conditions.
Okay.